Alright, in this section, section 3.4, they're going to talk about linear and angular speed, and they just want you familiar with it. It's something that we can now talk about because we're familiar with rotations and circles and angles. And so linear speed and angular speed are different. So linear speed is this linear path that's being taken here and how fast it's moving, right? If you remember, we defined s to be the arc length. Same reason they used the s as an angle before, because arc length was the same as the angle when you have a unit circle. But the angular speed is a little bit different. That's this insight, how the angle's changing as you go around. And so angular speed, they'll use the symbol omega. So omega is an angular type of speed that's here. So here's some definitions. So definitions: P is a point on a circle of radius r moving at a constant speed. The measure of how fast P is changing is the linear speed, v. So v is the linear speed, and it's simply the distance you travel, right, which in our case is arc length since we're traveling along a circle, over the time. So that's no difference than the distance equals rate times time format that you had before. Velocity is how far you travel over the time. How far we travel on a circle is arc length, so that's why it's that way. This isn't earth-shattering either. Omega is how far you've traveled in radians over the time it took you to do that. And what they want you to know is that there's a slick way to get the change in velocity. It's just r times omega. That's what, I mean, if you just put those things together, you know, let's actually put them together down here. So first things first, let me back up for just a minute. Speed, you already knew, how far you travel over time. Angular speed, how far the angle moves over time. And then what's very, very handy is this relationship down here, which is just putting a few ideas together. V is equal to how far you travel on the circle over the time. How far we travel on the circle is r theta over time. R then times theta over t would be the same thing, and that's r times omega. So sometimes they'll give us the angular speed, and all we have to do is multiply that times r in order to get the velocity of the point as it moves around. So everything that we're about to do is relating to these formulas, and it should be pretty nice as we go through. Find the angle generated by P in 10 seconds. So let me read the problem. Suppose that P is on a circle with radius 15 inches, and ray OP is rotating with an angular speed of pi over 12. Find the angle generated by P in 10 seconds. Okay, so what do we have? We have angular speed. Angular speed is omega. Omega is the angle which we want over the time which we have, 10 seconds. So the angular speed is pi over 12. And the rotation angle, we don't know. That's what they want. They want the angle generated in 10 seconds. And so we just multiply by 10, and we get theta is equal to 10 pi over 12. Or they'll reduce that down to 5 pi over 6. That's the angle movement in that 10 seconds, is 5 pi over 6. Find the distance traveled by P along the circle in 10 seconds. Well, the distance traveled is s. S is equal to r times theta. So that's coming from the previous section, right? The distance is the arc length. What's the radius? Well, we know what the radius is. The radius is 15 inches. What's the angle? 5 pi over 6. And so what do we get? Well, if I just stay with fractions, I can do, 2, 5, I can get 25 pi over 2. And it's a distance. What was the distance measured in? Inches. 25 pi over 2 inches is fine. If we want to see what that was as a decimal, I'm not sure how they're going to express it. Let's see what we have. 39.2. I'll do 39.27 inches. It's way close to that, right? Both of those are the same. I would accept either one. Find the linear speed Well, the linear speed is the velocity. The velocity is the distance traveled over the time. So what's the distance traveled? We traveled 25 pi over 2, and the time was in 10 seconds. Well, that's 25 pi over 20, 25 pi over 20, right? If I flip and multiply. And so what is that? That is 5 pi over 10, over 4. 5 pi over 4 inches per second. Okay, so again, that's 25 pi divided by 2 divided by 10. And we get that. Let me just take the 5 times pi, just making sure I did that simplification right. Yeah, so 5 pi over 4 inches per second, or what it works out to be is 3.93 inches per second, right? That's the speed of that, 3.93 inches per second. Now, v should also be able to be found by r times omega. And what's the r? The r was 15. What's omega that we found in that they told us? It was pi over 12. So it could have been as simple as taking 15 pi over 12, which if I divide both by 3 is 5 pi over 4. We could have come up with that a different way. So there's two ways to have gotten the velocity. Because we had all the numbers, I did it the traditional way, which is simply the distance traveled divided by time. Or we could take the velocity times, or we could take the, the radius times the angular speed. Either one would work in there, just to show you that that second formula works. So now we're going to get into some specific types of problems. We have a belt that runs on a pulley of radius 5 inches at 120 revolutions per minute. Find the angular speed of the pulley in radians per second. Okay, so we need to figure out how far it's moving. So a belt runs a pulley of radius 5 inches at 120 revolutions per minute. Now I got to do some work because they want per seconds. So in order to find out what they want, the angular speed, I got to figure out the angle that it travels all over the time. Right? And so what do we know right now? We know that it's making 120 revolutions, but that doesn't tell me the angle. What we need to remember is 1 revolution in terms of radians is 2 pi. And I got 120 of them. So the angle movement in 1 minute is 120. Sorry, I had 20 in my mind. 120 full rotations, or 240 pi is the angle that it's traveling. It went 240 pi in 1 minute. Well, I got a problem because they want it in radians per second. Right now I have radians per minute. So all I have to do to fix that is make my 1 minute the appropriate number of seconds. And when you look at that, you get 4 pi radians per second. It's making 2. Now, does that make sense? It's making 2 revolutions per second, which means in 60 seconds, it would have made 120 revolutions. So you want to look at it backwards and forwards and make sure it makes sense. Find the linear speed of the belt in inches per second. Well, the linear speed is simply r times omega. I could use s over t, but r times omega may be better because right now I know r, 5, and I know omega. Omega is 4 pi radians per second. And so what I get out of this is 20 pi inches per second. Now, I could have taken the time to find out what S is. I would have had to do another calculation, right? I would have had to do a side calculation of r theta. It wouldn't have been terrible. R would have been 15, theta was the 240 degrees, and the time would have been 60 seconds, and we would have gotten the exact same 20 pi inches per second. So you'll want to use whatever formula is fastest for you. So now we got a satellite. A satellite's traveling in a circular orbit approximately 1,800 kilometers above the Earth's surface, and it takes 2.5 hours to make a complete orbit. Okay, so let's talk about that. We want to approximate the linear speed in kilometers per hour. So in the end, we want to find the velocity. The velocity is, I could do it as s over t. I could also do it as v times the angular velocity. I'm sorry, the angular speed. But v is equal to s over t. Let's use that. Well, if we're going to get s is equal to r times theta. Perfect. So what's r? Well, we got to go out from the Earth's core, right? And so r is the 6,400 kilometers to get to the Earth's surface plus the 1,800. Otherwise, you're not doing a circle, you're doing some kind of strip arc, and it needs to be a complete central angle circle, and that's equal to 8,200. 8,200 kilometers is my radius. Again, here's the Earth, here's the orbit. In order for this to make sense, it's got to be a full circle, so that's where we're getting the 6,400 and the 1,800 added together to get out to that orbit. So there's a good visual of it. So now we know S is equal to, sorry, let me not do it up there. So now we know that S is equal to R, 8,200, times the angle that it takes it to make. Okay, and so what angle is it making? Well, in 2.5 hours, and they do want kilometers per hour, that's nice. In 2.4 hours, it makes a complete orbit. Well, a complete orbit is one rotation, which is 2 pi. So that's S. Well, if we're going to figure out V, we need to take the distance it travels. So this is the distance that satellite's going to travel, and it's going to take 2.5 hours to do so. And we grab a calculator, and we take 8,200 times the 2 pi and divide by 2.5. And when we do that, we get a nice velocity of 20608.8 kilometers per hour. So it's moving at 20,608.8 kilometers per hour. That's what we get when we take our 8,200 times the 2 pi and divide by 2.5. Approximate the distance the satellite travels in 3.5 hours. Okay, few ways to do this. So the distance it travels in 3.5 hours. Okay, so distance is equal to rate times time. Right? And so the distance it's traveling is equal to the rate that it travels, which is 20,608.8 times time, 3.5. Okay. And so we're doing nothing more than our old distance formula. It would make 20,608.8, and if we multiply that by 3.5, we get 72,130.8 kilometers would be the distance traveled in the 3.5 hours. Remember, in one rotation, the distance traveled was that 16,400 pi, which is 51,000. So yeah, I'm going farther, 72,130.8 kilometers. So you don't have to, there's not always the formula. It could be old knowledge base coming through. But these are applications of linear and angular velocity. You can take a look at the notes, right? You can bring notes to the exam. So do so for this as you feel it's needed. I'll give you a detailed explanation of what's going to be on the exam and what's not. All right. I hope this goes well for you, but check in with me if it doesn't. Thanks so much.